Yeah, we are live on YouTube now. Okay, there are still people entering the room, so maybe we wait 1 minute more and we start. Okay, so maybe, I don't know, Juan is not, anyway. So let's get started with the talk. So welcome everybody and good afternoon. I'm Ramon Aguado. I belong to the Spanish Research Council, FESIC, to the Material Science Institute in Madrid, and I will be chairing this session. Today it's a pleasure to introduce Professor Stefano Baroni from SISSA in Trieste, in Italy. Professor Baroni is a well-known expert in numerical methods applied to a lot of different systems in condensed matter and materials physics, and the boundaries also between physics and chemistry, including interfaces, semiconductors, chemical reactivity, catalysis, lattice dynamics, and a lot of different systems have been studied during his career. And he's also well known for being the main developer and main promoter of this quantum espresso software that allows to perform high-end and very sophisticated computation, numerical simulations of different materials and systems. So thank you for giving this talk, and please, the floor is yours, Professor Baroni.
Thank you very much for the kind introduction. Let me start by thanking the chairs of the conference, Maria Jose, Herman, and Jose Maria, for allowing me to be with you this afternoon, and all of the members of the organizing committee for the incredible job they have done and they are still doing to keep up with this very unusual emergency situation and for organizing in such a smooth and efficacious way this online version of the conference. So today I will talk about some studies that have been done in SISSA over the past 5 years or so to address the problem of the quantum mechanical simulation of transport in extended systems. We started from heat transport, as I shall briefly mention during my talk, but the main issue addressed in today's talk will be charge transport in ionic conductors. Let me first start by explaining the rules of the game and by explaining some sentences that I have written in the abstract and that may sound obscure to some or most of you. So what I'm going to address is the transport properties of collections of molecules or atoms that may carry an electric charge. When you apply an electric field to an ionic conductor, a current, an electric current will develop in response to the applied electric field, and to linear order, of course, the current will be proportional to the field, the constant of proportionality being the electric conductivity. For ionic conductors, the current is given essentially by the sum, by a combination of atomic or molecular contributions, each of which is the product of the velocity of the charge carrier, be it a molecule or an ion, times a rather fancy object that is called the Born effective charge of that atom. That is basically the derivative of the macroscopic dipole of the system that I call here mu with respect to the displacement of each atom. So this is a tensor quantity because it is the ratio, it is the incremental ratio of two vector quantities, the total dipole of the system and the displacement of each atom. The Green-Kubo theory of linear response essentially says that the conductivity can be expressed by the product of two terms. One is the equilibrium value of the fluctuations of the current, of course, in the absence of any applied field. So at equilibrium, you have the average current is 0, but you have thermal fluctuations of the current, and the expectation value of these thermal fluctuations is one of the two terms that enter the definition of the conductivity. The other term is the time it takes for each one of these current fluctuations to regress to equilibrium. This is a rather disguised form of the Green-Kubo formula that I will show in a while, but it is one form that is particularly meaningful because it says that sigma is essentially positive, being the product of two positive definite quantities, the variance of the current and the autocorrelation time. So the usual form of Green Kubo is actually that the conductivity is proportional to the time integral of the time correlation function of the currents, and these two expressions are essentially identical because the correlation time is defined as the ratio between the time correlation function and the expectation value of the square of the current. So let us now consider regular plain vanilla water. Of course, you have current fluctuations because these effective charges are different from zero, and because the current flickers all the time. Hence, this quantity here is non-null. It is strictly positive. Still, if you compute the integral of the autocorrelation time of the current, what you find is that this is positive for very short times, but then inexorably it decays to zero, not surprisingly, because pure water is an insulator. So we have a kind of conundrum due to the fact that you have non-vanishing fluctuating currents that gives rise of a strictly null or a strictly vanishing current. This conundrum can be extended to some extent if you go to a ionic system. I take here, for the sake of comparison, partial ionic water, where you have that the effective charges fluctuate. Effective charges are tensors, so you have the diagonal elements of this tensor that oscillate around some typical value that differ in oxygen and in hydrogen, whereas the off-diagonal components oscillate around zero, and they have their own statistical distribution. Here, I have drawn the autocorrelation functions of the currents computed in three different ways. The black curve is the expression that I have given before with the Born effective charges. And the blue and the dashed lines are currents computed with constant and scalar charges, computed in one case as the average of these effective charges, and in the other case, the way a chemist would do, just by associating the formal oxidation numbers of oxygen and hydrogen to the corresponding ions. So associating a charge +1 to hydrogen and a charge -2 to oxygen. What it turns out is that if you compute the integral of the autocorrelation time, that according to Green and Kubo is the conductivity, you find that the true conductivity, the formally exact conductivity given by the Born effective charges, coincides within numerical accuracy with the value you would obtain with the formal oxidation states, but would differ, not surprisingly, from what you would get with the average effective charges. So the surprise here is not just that the average charges don't work, there is no reason why they should, but that by replacing these very complicated Born effective charges that are time-dependent and tensor quantities with integer and time-independent numbers, you obtain the same conductivity within numerical error. So these authors, from which I have taken these figures, at some point in their papers state that, interestingly, the use of predefined constant charges can yield the same conductivity as is found with the fully time-dependent charge tensors, but only if they have the values z equal to 1 and z equal to -2 for hydrogen and oxygen, respectively. Not surprisingly, these are not random numbers. These are what a chemist would identify with the formal oxidation states of hydrogen and oxygen in water. So how come? In the first place, how can you define oxidation states? So the chemical definition is very hand-waving and does not lend itself to any computation. So essentially, chemists would say that the effective charges would be what the atomic charges would be if the ionic approximation would hold, but the ionic approximation doesn't hold. So there is no way of computing rigorously an effective charge out of this accepted chemical definition. So let us see how topology helps defining these oxidation states. So let us take a system made of ions that I have depicted here as red and green dots, put into a finite simulation cell that is the only thing we can afford numerically. Usually in computer simulations, we adopt periodic boundary conditions, which means that what we actually simulate is not an isolated system, but a collection of an infinite number of replicas of the same system. Because you have this periodicity, the geometry of the system, or I would say the topology of the system, is the same as the topology of the torus. Because if you go from one place here to another image, periodic image, what you would do is essentially a winding around one direction in the torus. So a very important concept in all of our arguments will be the concept of closed paths in configuration space that would correspond to closed loops on the torus. Here I have a closed path starting and ending at the same position in configuration space. Of course, because the system is periodic, when I have one closed path, what it is tacitly understood is that it is not just one path, but it is a collection of periodic replicas of that path that are all mapped onto a closed path on the torus. This is a closed path beginning and ending at the same point A in the configuration space, which basically is mapped onto a path on the torus that is called trivial. What a trivial means in this case is that it can be shrunk to a point without the need of breaking it, of cutting it. So this is the trivial paths are those that make no windings around any direction of the torus. Of course, you have to think of a configuration space of very high dimensionality of dimension 3n, where n is the number of atoms. Here for the sake of graphical clarity, I have assumed that the dimensionality is 2, but what you have to keep in mind is this very highly dimensional configuration space and tori. So this is a trivial path with no windings around any directions of the 3n torus, but you can as well think of non-trivial paths that start in a unit cell and end in a replica or in a periodic replica of that unit cell. Those paths are characterized by non-vanishing winding numbers. So this is a path with winding number 1 along one direction and 0 along the other direction. So here you make a full winding around this direction and no windings around this direction. So this path has winding numbers 1 and 0. Of course, in the plane, on the torus, this is it. But in the plane, you have to consider all the possible replicas of this elementary path, and this is what this path on the torus would look like once unfold in the plane. You can play more complex games. If you make a jump not of 1 unit cell but of 2 unit cells, this would correspond to 2 windings around one direction of the torus and 0 windings around another. But you can do many different things. So you can do a winding around one direction and another winding around another direction. To cut the long story short, all the closed paths in configuration space are characterized by a collection of winding numbers, and you have one for any directions in the 3n configuration space. Of course, you can have many different paths, actually an infinite number of them, that correspond to the same collection of winding numbers, and any pair of paths that have the same winding numbers can be deformed continuously one into the other without cutting the paths, any of the two paths. So let us consider now a closed path in configuration space, and let us think of some fictitious time dependence of the atomic configuration along this path. So you would have, oops, I'm sorry. As the system goes through a periodic path in configuration space along some fictitious time that we have used to parameterize this path, of course, the Hamiltonian would change along the path, because so do the atomic configurations, and the electronic Hamiltonian depends on the atomic configurations. But this Hamiltonian would be a periodic function of time because the path is closed. So now comes the other very important concept of our considerations, is that if you compute the time integral of the current, of the adiabatic current displaced along a closed path in configuration space, or alternatively along a period in the Hamiltonian, in the time-dependent Hamiltonian, this fundamental result by Thouless, established in the early 80s, says that this integral is quantized. Basically, the dipole, that is the integral of the current, can only be a multiple, an integer multiple of some quantity. So let us see what are the consequences of this on charge transport. If I consider a closed path in configuration space, that is a path that goes from a point in a unit cell to its periodic image in another unit cell, and if we assume that there's integer numbers that enter the Thouless quantization of charge transport are independent of the initial point and of the path itself, then you can demonstrate that this integral, which is the displaced dipole, is a linear combination with integer coefficients of the winding numbers. These integer coefficients are topological charges that are properties of individual atoms, and that can be formally identified with the atomic or ionic oxidation states. So let us make a first detour, a short detour on transport theory, and in order to highlight the next important ingredient of our consideration, that is what we call gauge invariance of transport, let me move laterally to heat transport. And in the theory of heat transport, essentially what you have is that the thermal conductivity has the same Green-Kubo expression as the electric conductivity, that is the integral of the autocorrelation time of what? Of an energy current. And an energy current can be defined in for classical systems in terms of atomic energies, EI. EI are atomic energies defined in such a way that the sum over all the atoms of the atomic energies is the total energy, and of their derivatives with respect to the ionic or atomic coordinates. Now, of course, this is good when you have a classical force field, but in modern computer simulations, one wants to compute the currents and properties from first principles. So the question naturally arises: what is the expression for this in density functional theory, or more generally in quantum mechanics? And until a few years back, it was commonly believed that, I just quote a sentence from this paper, the widely used Green-Kubo relation does not serve our purposes of computing the thermal conductivity, because in first principles calculations, it is impossible to uniquely decompose the total energy into individual contributions from each atom. And of course, this poses yet another problem, because we are used to think that whatever can be measured, at least in principle, can be computed from quantum mechanics and density functional theory. And now it appears that a quantity that can be easily measured in the lab, namely the thermal conductivity, cannot be computed from first principles, which I find rather unacceptable. And in order to solve this problem, let me just review what the problem is. And it is not a problem specific of quantum mechanics. It is the problem that goes with any first principles expression for the current. The current, so transport theory is basically the theory of transport of conserved quantities that are extensive, such as charge and energy, and that are conserved. So basically, extensiveness says that the energy or the charge, or you name it, associated to some domain in 3D volume is the sum of the value that the quantity would have in each subdomain. This is, of course, what you find in any thermodynamics textbooks, but this neglects the contribution of interface terms in the definition, in the partition of the energy. So when you partition the energy into the energy of a full system, into the energies of subdomains, you have to decide more or less arbitrarily how to partition the interaction energy that is localized at the interface. Of course, in the thermodynamic limit, this doesn't matter because the interface energy for short-range interactions vanishes in the thermodynamic limit. But when you want to define an energy density that is needed to compute currents and to make transport theory, you have to make a choice, on a microscopic choice, on how to partition this interaction energy. So basically, you have two guiding principles. One is extensiveness, that says that an extensive quantity can be written as the integral of some density, and one is conservation, that says that the time derivative of the density is the divergence of some vector field that you can identify with the current. Now, actually, all you require from this density is that its integral equals the total energy. So the density itself is not well defined. What is well defined is the integral. So any choice of the density that gives the same integral in the thermodynamic limit is equally good. So that densities that differ by the divergence of a bounded vector field whose integral all over the space vanishes are equally good. So the density is itself ill-defined modulo the divergence of a field. The current is ill-defined modulo the total time derivative of that field, and the integral of the density is equally ill-defined by the total time derivative of a vector. So let us go back to green cubo. We have oscillating currents, and we have the time correlation function. The integral of the time correlation function is the object of our dreams, is the conductivity. More than 1 century ago, Einstein, in a different context, when studying Brownian motion, arrived at the conclusion that the integral of some time correlation function, it was the velocity of a molecule in his case, or of a Brownian particle in his case, can be a current in our case, is essentially proportional to the expectation value of the integral of the quantity, so that the conductivity could as well be defined as the slope of the energy displacement, defined as the integral of the squared integral of the current versus time. So we have now two different expressions for the density. Gives rise to two different expressions for the current that differ by a total time derivative. And Einstein says that, Einstein and Green Cubo say that the transport coefficient is the ratio of the variance of this integral over time. Now, if you have the two expressions for the current, you have the two expressions for this integral, but because this is a total time derivative, the integral of P dot is bounded in space, so that the variance of D prime is equal to the variance of D plus the variance of delta P plus the covariance of D and delta P. This is of order 1 in the long time limit. This is of order T because the current is a diffusive process, and this is of the order T to the power 1/2, so that in the long time limit, these do not contribute to the Einstein-Green-Kubo expression for the conductivity. So we arrive at the conclusion that if two currents differ by a total time derivative, their conductivity, their transport coefficients would be equal to each other. So let me state this in full generality. Any two conserved densities that differ by the divergence of a bounded vector field are physically equivalent, and the corresponding conserved flux is different by a total time derivative, and the transport coefficients would coincide. So going back to our problem of computing the heat transport coefficients from first principle, the solution would be to choose any local representation of the energy that integrates to the correct value and whose correlations decay at large distance, and the resulting conductivity would be independent of the specific representation. This allows us to compute thermal conductivities from first principles, entirely from density functional theory. These are the values of the conductivities of water obtained with two different representations of the current. The two different representations forget the meaning of this horizontal axis and concentrate of the value of this function at 0. The value of this function at 0 is the conductivity that you see is independent of the correlation. It does not compare very well with experiments because it is well known that this is computed with density functional theory in the GGA approximation, and it is well known that the GGA makes water more viscous and more solid-like than it is in nature. So you would need dispersion force corrections to make the computations match with the experiment. So let us go back to our business, that is to understand why electric conductivities can be computed from oxidation states instead of from effective charges. So let us take the Einstein definition of the conductivity. It is the ratio of the squared dipole displaced along a molecular trajectory and time. This is a molecular trajectory in configuration space going from A to B, and we break this trajectory into two segments. One is a trajectory, is a fictitious trajectory that goes from A, from the initial configuration, to the periodic image of the initial configuration that lies in the same unit cell as the final configuration, plus the small segment joining the two. Of course, the dipole displaced is the sum of the dipole displaced from A and A prime and the one displaced from A prime and B. And playing the same game as we did in gauge invariance, we have that the variance of the true dipole is equal to the variance of the A prime dipole plus terms that in the thermodynamic limit do not contribute to the conductivity. Why have I introduced this fictitious trajectory from A to A prime? Because in this case, we can apply Thouless theorem, because A prime is a periodic image of A, and if we make a fictitious time parametrization of the Hamiltonian along the path, this parametrization would be time cyclic. Because of this, the dipole displaced along A and A prime can be expressed in terms of oxidation states, as I have tried to explain before. Concluding, we have that the long time limit of the ratio between the dipole, the square dipole, computed from the exact quantum mechanical definition in terms of effective charges, and the dipole computed from the atomic oxidation states, this long time limit coincide, and adiabatic conductivities can be calculated from the Green-Kubo theory of linear response in terms of integer, scalar, and time-independent topological atomic oxidation states, instead of from real tensor and time-dependent Born effective charges. So here is a few numerical experiments that Federico Grasselli and I have done a couple of years ago. This is a snapshot of a molecular dynamics run of a molten salt, and from this snapshot, we have selected one atom and we have displaced it cyclically, just one atom, and around from one unit cell to the other, making a loop in configuration space. What you obtain is that if we compute the dipole transported along this closed path, this is the time series of the Born effective charges. You see that this is a cation, a positive ion. The diagonal effective charge oscillates around 1, and the off diagonal oscillate around 0. And the dipole displaced along the direction along which we have moved the dipole sums integrates to 1. This is not nearly 1. This is 1 for mathematical topological reasons, and it is 1 within numerical accuracy, whereas the dipoles displaced along other directions would be 0. This is the displacement along when you move two different ions, one along one direction and one piercing this path pierces this phase here, and the blue one pierces this phase here. So one is positive, the other is negative. So the total dipole displaced along the z direction is 0, whereas the dipole displaced along the y direction is equal to the oxidation number of chlorine, that is -1. And you can keep playing games of this sort, and you will always fulfill these topological conditions. Here is the computation of the conductivity using the two different expressions for the current in terms of effective charges and of oxidation numbers, and we see that within numerical errors they coincide. So let us now consider what happens if your molten salt is non-stoichiometric. You have an excess of cations in this case. The excess of cations releases solvated electrons in the melt that I have depicted here in green. And if you let the dynamics go, you see that the solvated electron diffuses much faster than the ions, and this is depicted here. And this is the overlay of different configurations you see that the ions stay more or less in the same region of space, where in the same time where the desolvated electron essentially crosses the entire unit cell. If you play the same game as before of studying closed paths in configuration state, in configuration space, you will see that you have some paths for which the cation displays seemingly a positive unit oxidation states, as chemical intuition would suggest. But there are other paths that start from exactly the same configuration. This is start and end in the same configuration, but by choosing a different path, you manage to have a different displaced dipole, and so seemingly a different oxidation state. What happens? So the definition, the topological definition of dipole that we have, of oxidation state that we have given, builds on the hypothesis that the configuration space is how we say strongly adiabatic. This means that any closed path in configuration space can be shrunk to a point without ever crossing a region where the electronic gap of the system closes. So if this condition is fulfilled, the path, the dipole displaced along different paths, starting and ending in the same configuration, would be equal, and the dipole corresponding to a trivial path, that is starting and ending at the same configuration in the same unit cell, would be zero. But if you have regions where the electronic gap closes, then you can no longer conclude that the dipole is independent. The displaced dipole is independent of the path when the path is non-trivial, that is when it crosses the boundary between unit cell, or that it is zero when it does not, when it lies entirely within the unit cell. This is illustrated by a thought experiment here. Here we have 3 potassium ions and 1 chlorine, and we make a cyclic path that starts and ends in the same configuration. So it is totally closed, but you see that the dipole in this case is non-vanishing. So this is the same movie as before, but we have highlighted here in green the Wannier centers of the electron states, and you have basically 4 Wannier center per closed shell per ion, plus one Wannier center here that, as you will see in the animation that follows, will wander back and forth in the system. So that atom, that electron, is passed from one atom to the other that do not move. That is, this is a trajectory that carries an electric current without carrying any atomic current, any mass current. So this is the final slide of my presentation that highlights a comparison between the Einstein green cubo plots, that is the mean squared dipole displaced along a trajectory, computed with full effective charges in blue, and with the only ionic currents in green, and the ionic currents plus the current of the lone pair, of the lone electronic pair in green. You see that the atomic current is much the atomic current is much smaller. The atomic conductivity is much smaller than the full conductivity, and that most of the current is actually carried by the lone pairs, by the solvated electrons. So let me conclude. Transport coefficients are to a large extent independent of specific microscopic representation of the conserved densities and currents. This gauge invariance of transport coefficients makes it possible to compute thermal conductivities from density function theory using equilibrium ab initio molecular dynamics and the Green-Kubo formalism. Topological quantization of charge transport allows one to give a rigorous definition of the atomic oxidation states, and combining this definition with gauge invariance, we can rationalize the fact that we can compute charge transport coefficients from formal oxidation states rather than from Born effective charges. And non-stoichiometric solutions may breach strong adiabaticity, thus determine an adiabatic transport regime where charge can flow without any concomitant mass flow. So let me finally conclude by acknowledging support from the Max Center for Supercomputing, the European Max Center for Supercomputing Applications, the Quantum Espresso community, and of course, above all, my two young collaborators, Federico and Paolo. Thank you all for staying with me up to now.
Thank you very much, Stefano.
Sorry for being longer than
are there
was supposed to be.
No, it's okay. Very good talk and extremely interesting. So are there questions? You can unmute yourselves if you want to ask a question. Maybe I can start. So I come from a completely different community, you know, more quantum materials community, and we talk about, you know, topological insulators, topological superconductors, this kind of materials. And we are used to talk about symmetries and related topological invariance and so on. So can you also apply this kind of principles here? Because you are using essentially the same kind of language of these Fowler's pumps. And
we're using the same language, but so the topology you guys mostly refer to is the topology of the reciprocal space, where you have singularities, Dirac points, and so forth and so on. And in that case, symmetry, of course, plays a very important role. In our case, we are mainly concerned with the topological properties of the atomic configuration.
Yeah, I understand. But can you somehow exploit some symmetries of the configuration space, come up with some clever ideas and mimic this kind of properties and talk about, I don't know, some topological ionic insulator or something like this? Maybe it's a crazy question.
Great. I will keep you posted if I'll ever have such a clever idea as you suggest. I will keep you posted. I'm afraid I cannot satisfy your curiosity right now.
Okay, thank you. So, are there more questions? Let me check if there are questions in the chat. Okay, so if not, let's thank Stefano again. Thank you very much.
Thank you all. Thank you all, guys.
Very interesting.
Thank you all.
I have one question, Stefano.
Sure.
You have made the analogy with the diffusion process. In this case, it's of a charge. But from your movies, looks like more a Levy flight, right? Where the charge jumps from one ion to another in step sizes that depends, I guess, in the density of ions in the sample, right?
Well, actually, it is these solvated electrons actually diffuse, making jumps, but it's like it's more like the diffusion of impurities. It is true that the diffusion is made in jumps, but at the end of the long time behavior of the correlation function is linear in time. So it's a diffusive process.
Of course, but it is interesting because you have a regime in which is ballistic, right?
Of course, the short time behavior of any current is ballistic, and it becomes diffusive only within a fraction of picoseconds. But the short time behavior, as you say, is ballistic because the dynamics here is purely classical. It's Newton's equations of motion. But short time, so it is ballistic. Yeah.
Thank you.
Okay. Any further question? Okay, well, if not, let's thank Stefano again. Very nice.
Thank you, guys. Thank you, guys. And congratulations for the conference.
Thank you.